This week we're going to talk about the weather where we lived. So we're going to look at things like fronts, extratropical lows, high pressure systems, all the things we've talked about and how different of the variables interact to make. So let's just start by looking at the United States weather right now. So you can see here coming across western part of West Virginia into Kentucky and Tennessee now there's a cold front. Cold front just simply means the air is getting colder as the front passed. You can see temperatures are in the mid 40s over here in Indiana, 30s back in Wisconsin. Pretty cold air. And on the other side of the front, temperatures in the 70s. So I would call that a pretty powerful cold front. Back to the west, back in Dakotas and stuff, you can see a warm front moving north. Temperatures are in the 60s on one side of it, other side in the 50s, even some 40s up there. So you have your warm front. And when you have them coming together, many times you have extratropical lows, low pressure. You're all used to them. When they go move by, you usually have some form of bad weather. Well, extratropical lows are where temperatures have a significant change around it, and they're areas of low pressure that help to move these fronts along. They tend to bring in lots of bad weather. So this extratropical low was over eastern Montana at this time. And you can see temperatures on one side of it are in the 60s, another side are in the 30s, even the 20s, and even to the north, some teens. So think about it, there's 40 to 50 degrees of temperature contrast across a relatively short area here. So that is one of the keys to identifying an extratropical low. Many times we're all used to hearing about tropical weather systems such as hurricanes. Uh, they form without any temperature contrast. So I don't want you, when we talk about extratropical lows this week, discussing systems that have no temperature contrast as being extratropical, such as hurricanes. Extratropical means there is a temperature contrast. Hurricanes can become extratropical, and actually extratropical systems can become tropical. But we're going to look at, just keep it simple this week. If you look across the United States, you see lots of these lows going on. Several will be moving across the country throughout the week. So you shouldn't have much difficulty finding one to talk about. Interestingly, we talked last week about how divergence aloft helps these lows develop. Well, if I look at divergence today at 300 millibars, where the jet streak is, we know that divergence occurred on the left front quadrant. Well, here comes a jet. That's the left front quadrant. Notice how all the yellow indicates divergence. It's right across areas in Montana. And where we find the low pressure today? Right over Montana is where it was. So that jet of extratropical contributes to the development of this extratropical low. So let's look through some of the slides that go with this week. So we want to know what shapes the weather. Well, I could have showed you on there. You can see the different air masses. Air masses are where the fronts come together. On one side of the front, where the cold air was, we had a continental polar air mass. They generally come out of Canada. On the other side, we had a warm, much more moist air mass coming out of the Gulf or the tropical Atlantic, where there are more maritime tropical air masses. Then if you go up to the North Atlantic or the North Pacific, you get the maritime polar. They're kind of cold but moist. And finally, over the desert in the United States, the desert Southwest like New Mexico, West Texas and all, you can get continental tropical air masses that are dry and hot. Now, these are your basic air masses, simple enough. Where they join, where they come together, you have a warm front or cold front. Warm front if the warmer air mass is advancing, cold front if the colder air mass is advancing. And where they're more combined together is where the extratropical lows are coming in. So, interestingly, tropical air masses modify less than polar air masses. Why is that? Well, they tend to form over warmer areas, and when they're traveling, the bottom cools, but the air mass stabilizes, which keeps the whole profile of the air mass very more warm, moist. Here, for example, is a stationary front. So you have a cold air mass and a warm air mass coming together, not exactly moving at all. So it just sits there. We know warm air rises, so warm air rises up over the cold front. That's why well away from the front, you wind up with these cirrus clouds. Then as you get a little lower, the warm air is closer to the ground. You've changed to alto stratus clouds or even nimbostratus or stratus clouds down near the surface where it's warmer and raining. So warm air has risen over top of the cold air, and the slope of this air probably in the cold air is not real steep. So that just a gradual rainy event. Here's a warm front. Warm fronts want to be moving probably towards the north or northeast, bringing up lots of moisture, usually with it, and you get this precipitation developing out ahead of it. And believe it or not, the precipitation might start off as snow in the cold air mass, or even freezing rain. And as the warm front approaches, temperatures warm, and you wind up with more rain or just plain old rain. Cold air masses. Cold air is much denser. So believe it or not, you can't move a cold air mass out of the way unless it wants to be moved. Cold air masses are very dense. They tend to make the slope of the front very steep. So the air rises much faster along a cold front. If it's rising faster, it has a better chance to tap into some of that might be instability in the air. We wind up with more thunderstorms around cold fronts than with warm fronts. You can see here, the other week I had one of these fronts come out of the northeast down into the eastern United States. It went all the way down into the Carolinas. And west of the Appalachian Mountains, there was nothing. You were in beautiful weather out there. Okay, an occluded front. A little different than either of the other two. An occluded front occurs when a cold front, which normally moves faster than a warm front, reaches and overtakes a warm air mass. We know warm air is less dense, so that cold front is going to push that warm air along. So what you wind up with, say, ahead of the warm front, you have temperatures in the 40s, we'll say. In the warm air, you have temperatures in the 60s. Behind the warm air, where the cold front is, we have temperatures in the 20s. This cold front has caught up, pushed that 60-degree air aloft. So now we have temperatures in the 20s on one side of this occluded front and in the 40s on the other side. That is a cold occlusion. All that means is that temperatures coming into the area are colder than what was ahead of the warm front. Warm occlusion is just where, we flipped those temperatures, so you might have 40s coming in and 20s maybe ahead of that warm occlusion. And here you can see it, all the warm air is aloft, cold and cool. All right, extratropical cyclones have an interesting shape on satellite when you watch them develop. You have this divergence kind of interacts with a front, usually a warm or cold front along it, and develops low pressure at the surface. So the idea is that low is developing, pushing the cold air down further south, bringing warm air up further to the east. Notice the shape of the clouds beginning to look almost like a comma, and it really begins to look like it as it gets into the final stage of development. Also notice that initially you have a warm and a cold front. Later, you have more defined warm front, more north-south cold front, and eventually the cold front has overtaken the warm air, and you wind up with that occluded front, which begins to get bigger and covers more area. But you can see the evolution of these on satellite very clearly as they become more and more comma-shaped with time. So we're going to move along through this section pretty quickly here. Interestingly, Dr. Art Carlson at Penn State developed a different model than the Norwegian model to look at these kind of extratropical lows. He called it the conveyor belt model. So with that in mind, what he did was he took a conveyor of dry air coming in from the northwest along the jet to the southeast of the low. He pulls up warm conveyor belts of moisture. And then to the north of the low, he has a cold conveyor belt, which kind of runs from the east to the west. You wouldn't think about that, but it probably happens. And with they combine, interestingly, the warm moist air comes up, the cold conveyor belt actually lifts over that warm air and forms the comma head, pushing the air to the west and then back to the north. So it winds up forming that comma head. And sometimes in that comma head is where you get the most intense precipitation that lasts the longest. What you're getting is that warm, moist air coming up from the south, cooler air coming in from the north, combining together to give more unstable air and more precipitation. And different sectors of the extratropical cyclones have different type of precipitation. If I was going to tell you that you live in Mount Vernon, Ohio, and this, or eastern part of Ohio, we'll say, and I have a low pressure system moving up from the southwest, and that low is forecast to pass western Ohio, you're going to be initially in a cold sector. Warm front's eventually going to pass you. So you're going to might have started out a little bit of snow or freezing precip and then change to rain because the warm air is coming up, the low's moving west of you. However, I moved that low and switched it so it was coming up on the Ohio-West Virginia border. All of a sudden, you're in the cold sector the whole time. Now, instead of thinking about rain or freezing rain, you're thinking of mainly snow. So understanding exactly where these extratropical lows is going can make a huge difference in the forecast for your area. And here you can see the principal tracks. The Colorado lows pretty far south. The amount of precipitation that falls with these tracks is based on how close they are to a moisture source. So if I have a track from the South Pacific up the East Coast or from Texas up, I get lots of moisture coming out ahead of it because it's tapping into the Gulf and tapping into the Southeast Atlantic. Now, if I have something like the Alberta low, which Alberta clippers are typically called, they tend to move fast. They're way far north along the United States and Canadian border. So they just pick up that moisture there. So you don't wind up with much moisture at all for them. They don't add a lot of precipitation with them. All right, final point on these extratropical lows. Extratropical lows, I said, are cold. That means the temperature difference across them is great. And we know that pressure drops faster in cold air than it does in warm air. So therefore, the pressure surfaces are going to dip down more and more. You actually wind up with the most intense part of that low being aloft instead of near the surface. Now, if you have a weak one, you can see here, but warm core, the desert southwest of the United States get these in the summertime. Sometimes it's very arid. What they are caused by is that very intense heating of the ground. So we know that heating spreads the molecules across. They get less dense. They wind up with lower pressure. So that is what happens. Now, we also know that when this happens, pressure changes slower with height. So you wind up literally with high pressure aloft, an anticyclone. Exactly the opposite of an extratropical low. These warm core systems, hurricanes are a warm core system. Hurricanes have the most intense low pressure near the ground and gradually transitions to an anticyclone aloft. So, final little wind systems we're going to talk about here are sea breezes. If you go up by Lake Erie or Lake Michigan, especially in the late spring, the air on the land really warms up. Sun's getting pretty strong by late spring or early summer. However, the lake we know hasn't changed as much. So you wind up with a very extreme temperature contrast there. So what happens is the air moves from the ocean to the land, or the lake to the land, and you wind up with very strong breezes many times in the afternoon because of that. The same can happen at the beach. So sea breezes or lake breezes are most intense during the daytime and especially in spring and early summer. By fall, the temperatures are not as contrast there. You'll still have some, but you're not as strong. And at night, just the opposite occurs because the ocean or lake does not cool as fast. Land cools faster. Air sinks, moves back out over the water. Valleys are the other one, and mountains. So here you can see a mountain valley breeze, how they work. Oh, this is the final thing. You get some of this in West Virginia mountains, better chance of it out in the Rockies. And really you need high pressure over it because you don't want cold fronts coming in or other things. The more breeze from major circulations is going to mess this condition up. But when there's high pressure and all, this dictates how the air will move on the valleys to the mountains. And this is extremely useful for firefighters. When they're fighting fires in the mountains, which we know can happen, this is what they use to forecast how those fires are going to move. So, hope you got something out of this, and let me know if you have any questions.